All right, welcome everybody to this week's String Phenol seminar series. Our first speaker is Manki Kim from MIT, and he will tell us about D-1 instanton superpotentials in string theory. Please go ahead, Manki.
Great, thanks, Fabian. And first, I'd like to thank the organizers for inviting me to give a talk at String Phenol seminar series. Today, I'll talk about the D-1 instanton superpotential in string theory, and this talk is based on the recent paper that I posted on arXiv. Okay. So this is the plan of the talk. First, I'll talk about the introduction and then strategy to compute the D-1 instanton superpotential, and I'll go through F-theory and the Picard-Fuchs equations, and then I'll eventually conclude. Okay, now let us start. So in my opinion, one of the most profound challenges in string theory is to understand non-supersymmetric solutions of string theory. But this is a too difficult problem to solve directly. So one thing you can try is to take an intermediate step and study for the n equals 1 vacuum of string theory and then break SUSY eventually. And this is the approach that I'll take. So this amounts to computation of the Kähler potential and superpotential of the effective supergravity. And in this talk, I'll focus on type 2B superstring theory convectifications on Calabi-Yau-3 or antifolds, and the non-perturbative superpotential terms generated by Euclidean D-1 brings. So why do I care about the D-1 instantons? By definition, the D-1 instanton superpotential is exponentially suppressed at weak string coupling. So they're really tiny. So you can ask, why do you care? They're so tiny. Nevertheless, I like to argue that understanding the D-1 instanton superpotential is very important. One of the reasons why it is so important is due to the fact that the D-1 instanton superpotential is living compared to the Euclidean D3 brane superpotential at large string frame volume. Let's say you want to stabilize Kähler moduli, and because the computation of the corrections to the Kähler potential is very challenging, although it is not absolutely necessary, you can take a very conservative approach to stabilize Kähler moduli by stabilizing Kähler moduli at large string frame volume. Let's say you want to do that. Then for the consistency of the computation, you must compute the D-1 superpotential. And although there is more reason why I really care about the D-1 instanton superpotential. The other reason is that we don't really know whether or not the realistic string vector that could describe our universe are at small g string. So we really need to explore beyond the weakly coupled string theory regime. To do so, we need to compute G-string corrections to the effective action. And computing D-1 instanton is one step along this direction. So because this is going to be a rather technical thing, let me first explain the strategy. So the D-1 instanton superpotential is expected to be generated in a non-trivial flux background. So if you want to use the Walsh's CFT to compute the D-1 instanton superpotential, due to the fact that you need to include the flux, the computation will be very complicated. And I don't want to go through that difficulties, so I want to avoid this by using the F-theory convectification on a Calabi-Yau fourfold, and I'll study the D-1 instantons theory. The reason why I want to use the F-theory is due to the fact that the D-1 instanton effects are encoded in the classical geometry. And this is why I can use the classical flux superpotential of F-theory to compute the D-1 instanton superpotential. And this amounts to computing fourfold period, which I'll explain later in the talk, which could be computed by using the Picard-Fuchs equations. And then with this technology, as the first step, I'll place 47 branes on each of 7 plane and show that the D-1 instanton vanishes in this configuration. And I'll call this configuration the global set limit following the nice paper by Halvorsen, Long, and Sung. So let's talk about F-theory then. First, let me review the necessary ingredients of F-theory. F-theory convectification on a Calabi-Yau fourfold, which is an elliptic vibration of a B3, is understood as a strong coupling description of type 2B convectification on B3. In this talk, you can think of B3 as a Calabi-Yau 3 or antifold. The reason why the F-theory is so nice is because of the fact that the exodoulaton of type 2b is identified with the complex structure of the elliptic fiber. And this also means that we encode the 7-brane data in the geometry through the discriminant locus of the elliptic vibration. Generically, if you have F-theory compactification, you have a strong coupling description. So if you want to reproduce type 2b description, weakly coupled type 2b description, you can take the so-called Zen limit to reproduce weakly coupled type 2b. And using that, you can compute the G-string corrections to the type 2b string theory. So now let's talk about superpotential in F-theory. One thing that we know is that the curvature of the Calabi fourfold induces the 3-brane tadpole. So if you want to have a consistent compactification, you need to include some number of the 3-branes and some integral four-form flux G4. Let's say you turned on integral four-form flux G4, then this induces classical flux superpotential of F-theory. And omega Y4 is the unique holomorphic four-form of the Calabi fourfold, and this depends on complex structure moduli of Calabi fourfold. So in a way, this is why the classical flux potential only depends on complex structure moduli of the Calabi fourfold. And now this is a classical 3-level superpotential. So one can ask, what are the corrections to the flux superpotential? And thanks to the non-renormalization theorem, this flux superpotential doesn't receive any perturbative corrections. So the only corrections that can arise are due to non-perturbative effects. And the non-perturbative effects that can arise in F-theory come in 2 families. One is Euclidean M5 branes wrapped on vertical devices. By vertical, basically I mean that the Euclidean M5 brane wraps some elliptic fiber direction. And there is also a gauge inner condensation due to space filling M2 branes, which become D3 branes. If you take the Zen limit, the Euclidean M5 branes become Euclidean D3 branes. So this is clearly not the D-1 instantons. And gauge inner condensation due to M2 branes kind of looks like the D-1 instanton superpotential. But as the name suggests, it is not the D-1 instanton superpotential. And also, I'm not going to talk about the detail here, but typically if you have an M2 brane gauge inner condensation, the 1/5 of the M2 brane gauge inner condensation is order WD3. So now we're confused in a way because we don't see the D-1 instanton superpotential in F-theory description. So we should ask, where in this picture is the D-1 instanton superpotential? And as I claimed earlier, I'm going to explain how you can see the D-1 instanton superpotential in the classical flux superpotential. And to do so, I'm going to take the Zen limit. Under the Zen limit, the horizontal integral four-form flux G4 becomes a linear combination of NS and S3 form flux of type 2b, which is at H3, and the RR3 form flux of type 2b, which I denoted by F3. And then there is also a gauge flux on the D7 brane component. In the similar manner, you can take the Zen limit with the holomorphic four-form period. And what happens is that the four-fold period becomes a threefold period times a linear function in the exodoulaton plus exponentially suppressed corrections in G string. So this means that if you take the Zen limit, the F-theory flux superpotential becomes the sum of type 2b flux superpotential plus the D7 brane superpotential plus the D-1 instanton superpotential. So the point that you should take away from this slide is that if you want to compute the D-1 superpotential, one thing you can do is to compute flux superpotential of F-theory, take the Zen limit, and find the exponentially suppressed corrections in the flux superpotential. So I'm going to eventually share that the D-1 instanton superpotential is vanishing in the global Zen limit, but let me give you 2 arguments why you should not be surprised by the result. As I defined earlier, we defined the global center as the small g string limit, where all the D7 branes carry the SO8 gauge groups. Because the D7 brane charge in this configuration is locally cancelled, the axial turn of the compactification doesn't really vary in the compactification manifold. This, in a way, means that in the global center, the Calabi-Yau fourfold Y4 is topologically equivalent to X3, which is the Calabi-Yau threefold of the underlying type to be compactification times T2 multiplied by Z2. This also implies that in the global center, the fourfold period is just threefold period times a linear function of tau, which shows that there is no D-1 instanton superpotential. I'm going to sketch the proof of this statement using the Picard-Fuchs, but let me first look at the microphysics to convince you that even from the physics perspective, this is something that you should expect.
Can I ask a question real quick?
Sure.
The trivial example where you wouldn't even have D7 branes kind of falls also into this class, right? Because the dilaton?
That's true, but yeah, that is absolutely true. But I'm not really aware of a 307 plane orientable where you don't have any 7 plane.
With 307?
Yeah.
Not even on orbifolds? I would have thought you have some simple orbifold, at least at orbifold points. I don't know whether.
Oh, yeah, that could be true. But in this talk, I'm gonna just focus on smooth Calabi-Yau threefold and the orientable of it. So yeah, thank you for the question.
Thank you.
Okay, now let us look at the local patch around the SO8 D7 brane stack. And this argument is thanks to Jakob Moritz and Timo Weigand. To understand when the D-1 instanton is generated, let me displace a single D7 brane from the SO8 stack at finite G string. Then around the SO6 stack, which is a combination of 3 D7 brane plus O7 plane, you can compute 1 over G string, which is written as what is shown on the slide. And you find a very bizarre thing, because perturbatively, around the SO6 stack, you find that string coupling becomes negative. So something is awfully singular. Then the D-1 instantons come in rescue. What they do is to separate the SO6 stack into 2 mutually non-local 7 brane stacks, where those are separated by ZD7 times the D-1 instanton. And then this separation actually resolves the singularity in the G string. So one way you can understand the role of the D-1 superpotential is, or D-1 instanton is, that they act as an agent to resolve the singularity in G string. So if you have no singularity in G string, you may not expect to see those D-1 instantons. And this is why in the global sentiment, you don't see the D-1 instanton effect in a way. Okay, now let's talk about the Picard-Fuchs equations because we want to prove the statement using the classical geometry. So as I alluded earlier, what we want to do is to prove that fourfold period becomes threefold period times a linear function in tau. To do so, we need some general machinery, and I'll use the Picard-Fuchs, as I said. And let me explain what those Picard-Fuchs equations are. Those are basically linear partial differential equations satisfied by periods of the Calabi-Yau. In principle, if you have the Picard-Fuchs equations, you can use the mirror symmetry to compute and find the integral basis of the solutions, but I'm not going to do so here. Instead, I'll do a very minimalistic approach by choosing the boundary conditions that there is an A-cycle period of the fourfold that becomes the threefold cycle period plus some exponentially suppressed corrections in the Sen limit. And similarly, there is a B-cycle period that becomes tau times the threefold cycle period plus exponentially suppressed corrections. And show that with those boundary conditions, that the exponentially suppressed corrections vanish. And in fact, this agrees with the mirror symmetry. So, but you might be wondering, due to the following fact, in F-theory, we know that type 2B complex structure and the exoskeleton and the D7 brane moduli are all mixed up. And it's really difficult to see how these moduli are split. This is a real subtlety, and I want to avoid this subtlety. And to avoid the subtlety, I'll first construct an 307 orientifold of a Calabi-Yau threefold, a smooth Calabi-Yau threefold. And I'll construct an elliptic vibration over it and construct the F-theory lift as a complete intersection Calabi-Yau fourfold to make the splitting between type 2B complex structure and the exoskeleton manifest. With this construction in hand, I'll claim that in the global settlement, the Picard-Fuchs equations of Y4 split into the Picard-Fuchs equations of the Calabi-Yau threefold in the underlying type 2B, and the Picard-Fuchs equations of the elliptic fiber. And I'll show that this implies the D-1 instanton is vanishing. So this is going to be a long computation if I want to do an abstract manner. So I'll just take a very simple example and look at one parameter family of a Calabi-Yau threefold in a weighted projective space. So this is the equation of the Calabi-Yau threefold. X1 through X5 are homogeneous coordinates of the weighted projective space. Psi here is the complex structure of the type 2B. To construct an orientifold, I'll take an orientifold involution that sends X5 to minus X5. Then the only plane is in a 7 plane located at X5 is equal to 0. And I'll do one trick because I want to embed this Calabi-Yau orientifold as a hyperplane into some other toric variety. And to do so, I'll change the coordinates where I keep all the x1, x2, x3, x4, but I'll replace x5 squared with y5. By doing so, I can embed this Calabi-Yau orientifold into some other toric variety as a hyperplane. And before I move on to construct the elliptic vibration, let me make one comment. If you look at this Calabi-Yau orientifold, you may realize that you can treat this Calabi-Yau orientifold as just a P3. But I'm not going to do so here, because by doing so, you'll lose the information about the type 2B description, and then you're going to again suffer from the subtlety due to the mixing between type 2B and the exoskeleton. So I'm going to keep this presentation and directly construct an elliptic vibration over it. So here's the result. If you construct an elliptic vibration over this Calabi-Yau orientifold, you get this equation in addition to the orientifold equation. Y, X, Z are just the standard coordinates of the Weierstrass model. And T here can be understood as the D-1 instanton. The discriminant of the Weierstrass model is given by delta, which is proportional to Y5 to the 6. So in a way, you can now see that the only D7 brane here, or only D7 brane stack here is the SO8 stack. And this is why we get a constant or modulus for the exoskeleton. As I promised, this is the SO8 D7 brane stack, and the exoskeleton doesn't really vary in the compactification manifold. So what is the Picard-Fuchs equation in this case? I'm not going to derive the Picard-Fuchs here because it's going to be quite long. So you can look at my paper. As the result, the Picard-Fuchs equations you obtain are the following. We have exactly two Picard-Fuchs equations, one for exoskeleton and one for type 2B complex structure. And you see that the Picard-Fuchs equations are actually split. And this implies that for the period, if I want to study the period integral, I can use the separation of the variables and write the period integral as the product of the period that depends on the complex structure and the period that depends on the exoskeleton. And to study the effect of the D-1 instanton, I can simply focus on omega t, which depends on the exoskeleton. So, as I said, I'm going to require the minimal, yes?
You have 5 minutes.
Okay, great, thanks. I'm going to require the minimalistic condition and require that the A cycle period becomes 1 under the Sen limit, and the B cycle period becomes tau under the Sen limit. After requiring those boundary conditions, I obtain the following solutions. A cycle period is a hypergeometric function, and the B cycle period is tau times a hypergeometric function. And crucially, those hypergeometric functions contain T factors, which, if you think about it naively, you may think that, oh, there are D-1 instanton corrections, which is in contradiction with what I said. But I want to emphasize one thing before I move on. It is really important to note that the common factor in the period integral does not really affect the physics, and only the relative size between the period does affect the physics. So let me explain why that is the case. So we have the A cycle period and the B cycle period. And let me study the Keller potential with those period interval. Then the Keller potential it contains the factor that depends on the axial term and the factor that depends on the hypergeometric function. Now what you realize is that because of the fact that the good physical observable is e to the k half times the absolute value of period, we can freely perform the Keller transformation to get rid of this common factor. And after doing that, what you obtain is that the A cycle period is just 1 and the B cycle period is just tau. And as a result, we conclude that there is no D-1 instanton superpotential in the global Sen limit. And let me emphasize it again, this agrees with the mirror symmetry. So let me conclude. We studied the classical flux superpotential in F theory in the global Sen limit at finite G string. And we found that in the global Sen limit, the F theory flux superpotential is exactly the same as the type 2B flux superpotential. And this implies that the D-1 instanton superpotential and the D7 brane superpotential are exactly vanishing. The core idea behind the proof was to use the toric complete intersection description. And we're currently computing the D-1 superpotential at the generic D7 brane configuration. I think it'd be really interesting to study some heterotic superpotential with a similar technique. Thank you.
All right. Thank you very much, Manki, for the very nice talk. Are there questions? So, yeah, Arthur, please go ahead.
Yeah, so I have a very, very naive question. How do you know that this classical analysis exhausts any contributions which are non-perturbative or which are 1 over GS? I mean, I understand that you find the right contributions, but how do you know, after all, you are in M theory at 0 volume of the fiber, so things are not classically controlled, and I'm kind of confused. I'm worried that there could be further effects which you just don't see.
Do you think that the non-renormalization theorem is not correct when the fiber volume goes to 0, or are you thinking that there could be some additional sources that can generate the superpotential non-perturbatively? If the later, I think. No,
not for the sources. It could be some topological, some fluctuations of the geometry which are non-perturbative. I mean, how do I distinguish at 0 volume? I don't have, I don't have a well-defined perturbative expansion. So if something fluctuates and this effect adds up, I'm just not certain. I'm not saying that you're wrong. I just don't see a very clear argument.
I see. Yeah, that's a good point. Given that we don't really have the fundamental understanding of M theory, the only thing that I can say for now is that, okay, there are these extended objects, M2 branes and M5 branes. And so if there is anything that can really affect the superpotential in the 0 fiber volume, then it might be due to some M2 branes or M5 branes wrapping on some cycles. And if you have an M2 brane that wrapped on some vertical cycle that also wraps the entire electric fiber, then actually it becomes, so if you have the Sen limit, then you can not really be present because of the fact that in the type 2B geometry, there is no one cycle. So in this global Sen limit, at least M2 brane doesn't really affect the physics. I mean, the Euclidean M2 brane. And then in the similar manner, Euclidean M5 brane doesn't really affect the physics. But I'm not here to say that this is the entirety, because there could be some additional things that we don't really understand about M theory. So barring that, I think there is no way that additional effects can be generated.
I'm not sure how do you dismiss possible gravitational fluctuation of the gravity background itself. 11-dimensional geometry.
Yes, yes. You are thinking something like the KK instantons, or
KK monopole, something like that. Yes, yes. Some topological thing which I don't see in. It's not just wrapped M2 or M5, it's something more complicated.
Oh, I see. Yeah, I've got to admit that I haven't really thought carefully about the KK modes or the KK instantons or some other sources. That's a very good suggestion. I'm going to think about that. Thanks a lot.
Are there further questions? So maybe I can ask two very quick ones. So the first one, just to clarify, the point on the previous slide was just to say that sort of the torus, the complex structure of the torus is given by the ratio of the half periods. So sort of, and if you divide them, sort of J of tau as a function of the ratio of the half periods, that's constant, and then the Euclidean the ED minus 1 contribution is 0. I mean, I don't need supergravity to see this, right?
Could you say that again?
I do not need supergravity to see that this is true. I mean, I don't need to look at e to the k over 2.
Right, right. Yeah, this is a roundabout way of saying things, but yeah, I do agree with you that you don't really have to have a supergravity description.
Okay, thank you. And my second question is, so you mentioned briefly studying the heterotic dual. So
yes,
of course, so everything you did here was very much tailored towards taking the Sen limit, constructing something such that you split off the D7 brane and the complex structure moduli and so on. So if you wanted to look at the stable degeneration limit instead, you would have to probably do a lot of things different from the story you told us. Or
what I'm hoping is that if I really carefully think about the K3 vibration of Y4 and then think carefully about the stable degeneration limit that goes to heterotic string theory, maybe there is a way that we can do some similar computation. But yeah, this is just a speculation. I don't really have a very clean idea about what I can do.
Okay, thank you very much.
All right, can I stop sharing?
Yes, I don't see any other questions. And in the interest of time, we should also move on.